What if I told you that scattered across our own Milky Way are giant, natural clocks, and some of them spin hundreds of times every single second for decades, they've kept almost perfect time, like the most stable metronomes in the entire universe. But recently, scientists listening to these cosmic clocks noticed something off. A tiny, collective wobble in their perfect rhythm. And this wasn't some flaw in the clocks. It was a signal from the depths of the universe, a message carried on the very fabric of space-time. It was the first whisper from a new, invisible cosmos, revealing a secret we were never meant to see. So, to get this secret, you first have to understand the clocks themselves. They're called pulsars. Picture a star way bigger than our sun that's reaching the end of its life. It doesn't just fizzle out. It collapses under its own crushing gravity, squeezing its core into an object so dense it's hard to even imagine. You're left with a sphere the size of a city, but a single spoonful of it would weigh as much as a mountain. That's a neutron star. Now, some of these neutron stars are born spinning ridiculously fast, and as they spin, they blast out powerful beams of radio waves from their magnetic poles. If one of those beams happens to sweep past Earth, our radio telescopes see a pulse. Blink, blink, blink. A handful of these, called millisecond pulsars, spin so fast and so consistently that they are more predictable than the best atomic clocks we have here on Earth. For years, astronomers just used them as landmarks in the galactic dark. But a few brilliant scientists, like the late Donald Backer, realized they could be so much more. They saw that a whole network of them could be turned into a scientific instrument of impossible scale, a gravitational wave detector the size of our entire galaxy. The idea they came up with is as brilliant as it is audacious. It's called a pulsar timing array. For more than 15 years, huge international teams, like the Nanograv project in North America, have been patiently and precisely tracking the signals from dozens of these millisecond pulsars. Their whole goal was to hunt for tiny, almost invisible shifts in the arrival times of their pulses. But why would these hyper-precise clocks ever drift? The answer, as it so often does, goes back to Albert Einstein. Over 100 years ago, he told us that space and time aren't just an empty stage, but a dynamic fabric called spacetime. He also predicted that the most violent events in the universe, like two giant objects circling each other, wouldn't happen quietly. They would literally create ripples in this fabric, waves of gravitational energy that stretch and squeeze spacetime itself as they fly across the cosmos. And that's exactly what the pulsar timing array was built to find. Imagine a gravitational wave, born from some cataclysm millions of light years away, washing through our corner of the galaxy. As this wave passes between us and a pulsar, it ever so gently stretches the fabric of space. This makes the path the pulsar's signal has to travel just a little bit longer, and the pulse arrives a fraction of a second late. Then, as the wave continues, spacetime gets squeezed, the path gets shorter, and the pulse shows up a tiny bit early. With any single pulsar, the effect is almost impossibly small and gets buried in other noise. But here's the genius part: a gravitational wave would affect all the pulsars in the array in a very specific, correlated way. The pattern of these tiny delays and advances across the whole sky would create a unique signature that could only be one thing: gravitational waves. For years, the scientists looked. They saw hints of something, a weird hum in their data, but the evidence just wasn't strong enough. Then, after 15 long years of staring at the data, it happened. The signal finally climbed out of the noise. And it wasn't just one group. Collaborations around the world, Nanograv, the European Pulsar Timing Array, and others in Australia and China all reported the exact same thing. They had found it. Not just a single wave from one event, but something way bigger, a constant, overlapping chorus of gravitational waves coming from every direction at once. People have described it as a background hum, like the universe itself is humming a low, constant note. It turns out, the cosmos is filled with these very low-frequency gravitational waves. This isn't like the quick, high-frequency chirps that observatories like LIGO detect from black holes crashing into each other. This is a much slower, deeper rumble, with waves that take years, even decades, to pass by. The giant space clocks actually worked. They had detected the gravitational wave background of the universe. So, what's making this sound? The leading explanation is about as epic as the discovery itself: supermassive black holes. At the heart of almost every big galaxy, including our own, there's a black hole millions or even billions of times more massive than the Sun. And a very common event in the cosmos is galaxies merging. When they do, their central black holes start a slow, cosmic dance, orbiting each other for millions of years and spiraling closer and closer. As they do this, they're constantly churning space-time, sending out these long, slow gravitational waves. The hum everyone detected is thought to be the combined sound of hundreds of thousands, maybe millions, of these supermassive black hole pairs, all dancing, all across the universe, all adding their voices to this incredible cosmic symphony. This discovery is just a monumental achievement. It's the payoff for decades of work from hundreds of scientists all over the world. And this isn't an ending. It's the very first page of a brand new chapter in astronomy. If you find this kind of cosmic detective work as amazing as I do, maybe subscribe and stick around for the journey. We are just now learning how to listen to the universe in this new way, and the secrets it's about to tell are just beginning to be heard. This is so much more than just proving a theory. Finding the gravitational wave background is like opening a brand new window on the universe. Think about it. For all of history, we've studied the cosmos by looking at light. We built bigger and better telescopes for visible light, radio waves, X-rays. You name it. But light gets blocked by gas and dust. And some of the biggest events in the universe happen without making any light at all. Gravitational waves are different. They sail through the universe almost completely untouched. They carry raw information straight from the heart of cosmic events that were totally invisible to us before. With this new tool, we can now watch the final stages of galaxy mergers. We can learn how these monster black holes grow and finally combine, which is a huge piece of the puzzle of how the universe got to be the way it is today. It's a completely new way to map the unseen structure of everything. This discovery gives us a new sense, a new way to listen. We can now hear the slow, inevitable death spiral of the biggest things in the universe. By studying this hum, how loud it is, what its pitch is, we can learn about all the supermassive black holes throughout cosmic history. Are they bigger than we thought? Do they merge more often than our theories say? The first bits of data already hint that the hum is a little louder than expected, which could mean supermassive black holes are more massive or merge more easily than we calculated. But like any great discovery, this one opens up even bigger questions. While the chorus of merging black holes is the number one suspect for this hum, it might not be the only thing playing in the orchestra. Some scientists have pointed out that the exact color of this sound doesn't perfectly match the simplest models. And that has kicked the door open for more exotic ideas. Could some of this signal be an echo from the very early universe, just moments after the Big Bang? Some theories say that things like cosmic strings, which are hypothetical, one-dimensional cracks in spacetime or huge phase transitions in the primordial soup, could also create a background of gravitational waves. In fact, one analysis suggested a model involving an early universe phase transition might even fit the data slightly better than the black hole model. For now, supermassive black holes are still the most likely answer. But the beautiful part is, we now have a way to actually test these wild ideas. As the pulsar timing arrays gather more data, add more pulsars to the network, and combine their results, the picture will get sharper. We'll be able to tell the difference between these possible sources, and maybe even pick out individual, loud supermassive black hole pairs from the cosmic choir. We turned our galaxy into a giant scientific instrument, and with it, we have heard the faint, constant hum of the cosmos, a sound that has been traveling across space for eons, carrying the secrets of dying stars and dancing black holes. The space clocks ticked out of rhythm, and in doing so, they gave us a new rhythm to listen to, the heartbeat of the universe itself.